All right, get ready because today on Talk Tensors, we are taking a deep dive into a paper that could really shake things up in the world of image segmentation.
It's a fascinating one for sure.
It's called Rethinking Decoders for Transformer-based Semantic Segmentation, a compression perspective.
Oh yeah, this paper's getting a lot of attention.
It is.
And for good reason, it's tackling a really fundamental problem in computer vision.
Yeah, so image segmentation, just to quickly remind everybody, it's basically about teaching AI to understand what's in an image by labeling all the different objects,
Oh,
right?
exactly. You got it.
Like if we gave an AI a picture, a busy street, it would be able to color code all the pedestrians, the cars, all the buildings.
Yeah, and all the different parts of the buildings too, like windows and doors.
Right, all the little details.
Yeah, the finer points.
And this paper is introducing a new way to approach segmentation using DPCs, which stands for decoder for principled semantic segmentation.
And it's all about approaching segmentation from a compression perspective.
Yeah, that's what makes this paper so interesting to me.
It really is a unique approach.
It's connecting this idea of compression from information theory to a visual task, which is image segmentation.
A great example of bridging different fields and getting really interesting results.
I mean, yeah, it's like we're taking something that's normally associated with making files smaller and applying it to understanding images.
Exactly. And it's working surprisingly well.
Okay, but before we get into DPCT, I think it would be helpful to understand how we even got here.
Yeah, let's do a little history lesson.
Can you walk us through some of the key milestones in image segmentation that led to this paper?
Sure. So image segmentation has been a hot research topic for a long time.
Yeah, decades at this point.
Early on, the techniques were pretty simple. Things like edge detection and thresholding.
Yeah, so just finding the outlines of objects.
Yeah, and then using thresholds to decide which pixels belong to which object based on things like brightness or color.
Okay, so they were good for simple images. But what happened when things got more complicated?
Right. Well, those methods struggled with complex scenes, overlapping objects, different textures, things like that.
Because those simple methods were pretty brittle, weren't they?
Very much so.
It seems like a pretty limited approach in hindsight.
Definitely.
So what changed the game?
Well, that's when machine learning really started to revolutionize the field.
That makes sense.
Researchers started training models on massive data sets of labeled images, allowing the models to learn complex patterns.
Yeah, so the AI was able to figure out all the nuances of an image that were just too hard to code by hand.
Exactly. That's the power of machine learning.
Okay, and this led to the development of convolutional neural networks, right?
Absolutely. CNNs became the go-to for a lot of vision tasks, especially image segmentation.
And why was that?
Well, they're specifically designed to process data in a grid-like structure, which images obviously are.
That makes sense.
So they were much better at recognizing objects in all sorts of different contexts.
Okay, so CNNs were the big breakthrough, but they weren't perfect, right?
Right. They do have some limitations.
Like what?
One of the big ones is that they can be computationally expensive.
Yeah, needing a lot of processing power and memory.
Exactly.
And this is where the concept of compression comes in, right?
Precisely.
If we can find a way to condense the information in an image without losing the important stuff,
We can make these models much faster and more efficient.
it seems like we're always trying to find that balance between accuracy and efficiency.
Absolutely. It's a constant trade-off in this field.
So efficiency is one of the motivations behind this paper.
For sure.
But there's also another term that keeps popping up, attention.
Yes, attention.
What exactly is that and why is it relevant here?
Okay, so attention is this really powerful mechanism in AI
Okay.
that allows models to focus on the parts of the input that are most important for whatever task they are trying to do.
So if we're looking at an image, it's like the model is able to ignore all the background noise.
Yeah, and just focus on the objects we're interested in segmenting.
That's pretty cool.
It's like having a spotlight that highlights only the relevant information.
And this is important for efficiency, I'm guessing.
Exactly. If the model can just focus on the important features.
It doesn't waste time processing all the irrelevant stuff.
Exactly.
So we've got CNNs dominating the segmentation world.
Right.
But they are a bit power hungry.
Yeah, they can be.
And then we have this growing interest in making things more efficient.
Yes.
Through things like compression and attention.
Exactly.
And that brings us to DPCT.
Right.
Which seems to be combining these ideas in a very unique way.
A very clever way.
And it takes inspiration from a classic technique called principal component analysis, or PCA.
Right.
And PCA, just to make sure everyone's on the same page, it's a mathematical tool for dimensionality reduction.
Yeah, basically finding a more compact way to represent data.
So it's like taking a high-resolution image and shrinking it down to a smaller file size.
Yeah, it's a good analogy, but instead of pixels, we're talking about abstract dimensions of data.
So PCA is all about finding the most important dimensions, right?
Exactly, the ones that capture the most information.
And DPT uses PCA to figure out which parts of the image are most important for segmentation.
Well, it's inspired by PCA, but it doesn't use it directly.
Okay.
Instead, it uses PCA as inspiration to develop its own way of compressing the image's information specifically for segmentation.
So it's like PCA is the starting point,
Right.
but DPT takes it to the next level.
Precisely.
So how does it actually do that?
It's a two-step process.
Okay, walk me through it.
First, it constructs what they call in the paper the ideal subspace,
The ideal subspace.
which is
then.
basically a compressed version of the image that is optimized for segmentation.
So DPT is figuring out the best way to organize all the visual information
You got it.
so that it's easier to actually label the different objects.
Right, like we talked about with attention, it's all about focusing on the most important stuff.
And to do this, they use a modified version of the multi-head subspace self-attention operator, or MSSA. Now, I don't think we need to get into all the technical details of that right now.
Right.
But the key takeaway is that MSSA is the architect of DPT's compression scheme.
A good way to put it.
It's figuring out the best way to organize all that visual information.
Yep, like putting all the pieces of a puzzle together in a way that makes sense.
Okay, so that's the first step. What about the second?
The second step is where the actual labeling happens.
Okay.
Once DPT has this nicely organized subspace,
Right.
it then uses another operator called multi-head subspace cross-attention, or MSCA, to find the best labels for the different objects.
So MSCA is like DPT's label maker.
I like that analogy.
Yeah, it's looking at all the compressed information
Yes.
and saying, okay, this group of pixels is probably a cat, this group is probably a tree, and so on.
Exactly.
It's figuring out which label best fits each part of the image.
Right. It's using attention to connect the compressed image features to the right labels.
Okay, so all of this sounds very impressive in theory,
It does.
but does it actually work?
That's the big question, right?
Does DPCT live up to the hype?
Well, the researchers put it to the test on a standard benchmark dataset called ADE20K.
80/20K.
Okay, which has all sorts of images with very complex scenes, lots of different objects, different lighting conditions, the whole works.
Okay, a real challenge then.
Definitely. And DPCT consistently outperformed other models across the board.
Really?
And not just by a little bit, it achieved significantly higher accuracy.
So it's not just a theoretical concept, it actually delivers results.
Oh, yeah. And not only did it achieve higher accuracy, it did it with fewer resources.
Fewer resources.
Less memory, less processing power, which is a big deal.
Yeah, especially as we're pushing towards more complex AI models.
For sure. Efficiency is going to be increasingly important going forward.
So DPCT's efficiency is a major advantage,
Yeah.
especially for applications where you need things to happen in real time, like self-driving cars.
Exactly. Any situation where speed is critical.
Okay, so we've established that DPCT works really well, but I'm still curious about why it works so well.
Yeah, what's going on under the hood that allows it to outperform other models?
What are the secrets of DPCT's success?
Well, that's where things get really interesting, and that's what we'll be diving into in part 2 of this deep dive.
Okay, I'm already hooked. I can't wait to hear more.
Stay tuned, because we're about to unravel the secrets of DPCT's remarkable performance.
All right, we'll be right back after a short break.
Welcome back to Talk Tensors. Last time we left off with DPCT's impressive performance on that ADE20K dataset.
Right, higher accuracy, fewer
This
resources.
is a really impressive achievement.
So what is the secret sauce? What makes this compression-based approach so effective?
Well, one of the key insights of this paper is how DPCT leverages the concept of orthogonality.
Orthogonality, okay.
Now, before you tune out, let me explain why this is so cool.
Okay, I'm listening.
Imagine you have a toolbox, right?
Okay,
And each tool in that toolbox has a very specific purpose.
makes sense.
You wouldn't want a hammer that also tries to be a screwdriver, right?
Right, you'd want specialized tools.
Exactly. You want the best tool for the job.
Okay,
And in some AI models, that's kind of what happens.
they try to do too much.
Well, the different parts of the model can end up with overlapping functions,
Okay,
which makes them inefficient and unstable.
so it's like having a messy toolbox where all the tools are jumbled together.
Yeah, it's hard to find the right tool for the job.
Okay, so how does DPC solve this problem?
Well, DPCT, through its use of compression and attention, encourages a more organized orthogonal representation.
Orthogonal meaning.
It's like each part of the model has its own distinct role,
Okay.
with very little overlap or redundancy.
So it's like each tool in the toolbox has its own specific purpose, and they don't interfere with each other.
Exactly, a well-organized toolbox.
I like that analogy.
And this orthogonal representation has a couple of amazing benefits.
Okay, like what?
First, it makes DPTT incredibly robust.
Robust how?
So remember how we talked about it being like a sturdy shelf that can handle some jostling?
Right, it's not easily broken.
Well, that's because each feature is represented in a distinct, independent way.
Okay.
So even if one part of the model gets a bit messed up, the other parts can still function properly.
So going back to the toolbox analogy, it's like if one tool breaks, you can still use the other tools without any problems.
Exactly. The whole system isn't compromised.
And that's really important for real-world applications.
Absolutely. Things don't always go perfectly in the real world.
Right? You need models that can handle unexpected situations.
And DPCT can do that.
So that's robustness. What's the other benefit?
The second benefit is efficiency.
Okay.
Because each feature is represented in this compact, independent way, the model doesn't have to waste time and energy processing redundant information.
It's like you've streamlined your toolbox, removing all the unnecessary duplicates.
Yes, exactly.
And that makes it much faster and more efficient.
Precisely. And this is a huge advantage when you're working with limited resources.
Like in mobile devices or embedded systems.
Right, where you don't have a lot of processing power or memory to spare.
This orthogonality concept is really fascinating.
It is. It's a key part of what makes DPCT so unique.
But how does DPCT actually achieve this orthogonality?
That's a great question, and this is where things get even more interesting.
Okay, I'm ready.
So the researchers believe that this orthogonality emerges naturally.
Naturally.
Yeah, as a side effect of DPCT's compression process.
Okay, remind me about the compression process again.
Right, so DPCT is all about minimizing what's called the coding rate,
Coding rate, okay.
which is basically a measure of how efficiently information is being represented.
Okay.
A low coding rate means you're representing the information very compactly, like a ZIP file.
Right, so it's like shrinking a large file down to a much smaller size.
Exactly.
Okay, so DPT is trying to achieve a low coding rate.
Precisely. It wants to represent the image's information as efficiently as possible.
And this leads to orthogonality.
That's what they found.
So it's like DPCT is striving for elegance and simplicity in its representations.
You could say that.
And in doing so, it ends up with this beautifully organized orthogonal structure.
Exactly. It's like it's discovered a hidden law of nature.
A law of efficient information processing.
Exactly. It's really quite remarkable.
This is mind-blowing. It's like DPCT is not just a model. It's a window into how information can be organized in the most efficient way.
I agree. It's a very profound insight.
So we've talked about the theory behind DPCT.
Right.
But let's talk about the practical implications.
Yeah.
What are some real-world applications that could benefit from this approach?
Oh, the possibilities are vast.
Give me some examples.
Well, imagine applying DPCT to medical imaging,
Okay.
where accurate and efficient segmentation is crucial.
Right, for diagnosing and treating disease.
Exactly. For example, you could use DPCT to automatically segment tumors in MRI scans
That'd be huge.
or to identify blockages in blood vessels.
So DPCT could help doctors make faster and more accurate diagnoses?
Absolutely. And it's not just about speed and accuracy.
What else?
DPCT's robustness could also be a game changer in medical settings.
Because you don't always have perfect images in medicine.
Right. The quality of images can vary a lot.
So you need a model that can handle noise and variations in the input.
Exactly. And DPCT can do that.
Okay, so medical imaging is a big one.
It is.
What other fields could DPCT impact?
Well, think about satellite imagery analysis.
Okay,
We're collecting massive amounts of data from satellites every day.
right.
And DPCT could help us make sense of it all more efficiently.
Like how?
Well, you could use it to automatically identify deforestation patterns,
Interesting.
or to track the movement of glaciers, or even to monitor urban sprawl.
So DPCT could be a powerful tool for environmental monitoring.
Absolutely. And its efficiency would also make it valuable in real-time applications.
Right.
Disaster response, search and rescue operations, things like that.
Okay.
Imagine using DPCT to quickly analyze aerial images of a disaster zone.
And identify areas where people might be trapped.
Exactly.
Wow. That's a powerful example of how DPCT could actually save lives.
And these are just a few examples.
Right. The potential applications are huge.
Spanning across so many different fields.
This is all incredibly exciting.
It is. It's a very promising area of research.
But I'm also wondering about the limitations of DPCT.
Sure.
Every breakthrough has its challenges, right? What are some of the hurdles that researchers still need to overcome?
Right, well, DPCT is amazing, but it's not perfect.
Okay. What are some of the limitations?
Well, one of the main ones is that it's primarily designed for static images.
So still images.
Yes.
But what about video?
That's a challenge. To apply this approach to video, we'd need to find a way to incorporate temporal information,
Temporal meaning.
how things change over time.
Right, like the sequence of frames in a video.
Exactly.
So it's like adding a whole new dimension to the puzzle.
It is. It's a significant challenge, but it's one that researchers are actively working on.
Okay, so handling temporal information is one hurdle. What else?
Another area for improvement is in handling fine-grained details.
Fine-grained details, okay?
DPCT is great at segmenting large objects, but it can sometimes struggle with small or intricate objects.
Where subtle details can make a big difference.
Exactly.
So it's like DPCT can see the forest, but might miss some of the individual trees.
That's a good analogy.
And this is important for things like medical imaging and robotics.
Absolutely. Any application where precision is key.
Okay, so handling temporal information and improving fine-grained segmentation.
Those are two of the big challenges.
Are there any other limitations we should be aware of?
Well, another potential concern is the computational cost of training DPCT.
Okay.
While it's very efficient to run, training it can still require a lot of computational resources.
So it's a trade-off.
In a way, yes.
It's efficient to use, but it takes a lot of power to train.
That's right. But again, researchers are working on making the training process more efficient.
It sounds like there's a lot of exciting work ahead.
Oh, absolutely.
As researchers continue to build on DPCT's foundation,
Yes, and push the boundaries of image segmentation even further.
I'm really looking forward to seeing what they come up with next.
Me too. It's a very exciting time to be working in this field.
All right, welcome back to Talk Tensors. We've been talking all about DPCT and how it's changing the game for image segmentation.
It's pretty groundbreaking stuff.
But now it's time for my favorite part of the show.
Oh, you mean novel notions.
Exactly. Time to get those creative juices flowing.
Always fun to speculate a little.
So what wild ideas has this paper sparked for you? What are your novel notions?
Well, this paper got me thinking, what if DPCT's approach isn't just limited to segmentation?
Okay, expand on that.
What if this whole compression idea hints at a deeper principle for how we build AI models in general?
Okay, now you're really intriguing me.
Imagine AI models that, instead of just gobbling up all the data they're given,
Right.
they first learn to extract the most important information, like the essence of the data.
So it's like they're learning to be more discerning, more selective about what they focus on.
Exactly. It's like teaching them to find the signal in all the noise.
That's a really interesting thought.
It could have huge implications for AI, making models more efficient, more robust, maybe even more ethical.
Okay, I'm hooked. But how would we actually implement that? How do we teach models to be more selective with data?
Well, one idea that I've been playing around with is inspired by DPCT's use of self-attention.
Okay.
What if we built models with a dedicated compression module at the front end?
A compression module, what would that do?
It would learn to extract the most relevant information from the input before passing it on to the rest of the model.
So it's like a filter that sieves out all the irrelevant stuff.
Precisely, leaving only the good stuff for the model to process.
That makes a lot of sense.
And this compression module wouldn't be fixed, it would be trained along with the rest of the model, learning how to best compress the data for a specific task.
So it would be like a dynamic filter, constantly adapting to the data.
Exactly, always learning and improving.
And this could have benefits beyond just efficiency, right?
Oh, absolutely.
You mentioned robustness and ethical consideration.
Right, so when a model is forced to focus on the most essential information,
Okay,
it's less likely to be fooled by irrelevant details or noise.
makes sense.
This could make it more robust to adversarial attacks.
Adversarial attacks, those are the ones where someone tries to trick the model, right?
Exactly. They introduce subtle perturbations to the input to try to throw the model off.
But if the model is only focusing on the most important information,
It's less likely to be fooled by those perturbations.
that's pretty cool. So compression could actually make models more secure.
It's a possibility, and it could also help with bias mitigation.
Bias mitigation, how so?
Well, if we can train models to focus on the truly relevant information,
Right.
they're less likely to pick up on spurious correlations or biases in the data.
So they're less likely to make unfair or discriminatory decisions.
Exactly. It's all about making sure the model is focusing on the right things.
This mindful AI concept you're describing,
That's a catchy name, isn't it?
It really is. It's like we're not just building AI that's smart.
Right.
Building AI that's thoughtful, that understands the nuances of the data.
I like that. AI that's more aware of the world.
And DPCT, with its focus on compression, feels like a step in that direction.
It definitely does. It's pointing us towards a new way of thinking about AI.
Well, on that note, I think it's time to wrap up this deep dive into DPCT.
Time flies when you're having fun with segmentation.
It really does. We covered a lot of ground today, from compression and attention to orthogonality and even some mind-bending novel notions.
We even managed to squeeze in a bit of philosophy.
A little bit, but that's what makes this field so fascinating. It's not just about the technology.
Right. It's about the bigger questions, how we understand intelligence, how we build systems that can learn and adapt.
And how we use those systems to make the world a better place.
Exactly. So to our listeners, if you're interested in learning more about DPCT,
Be sure to check out the link to the paper in the show notes.
we always love to hear from you, so let us know what you think.
What wild ideas has this paper sparked for you?
What are your novel notions?
Until next time, keep those neurons firing, and we'll catch you on the next deep dive.